All right, so in this video, we're going to do some examples for doing proofs with trigonometric identities, and we're going to talk about some tips and things and various strategies that you can use to complete these problems. So the idea here is we want to be able to do these proofs to help practice manipulating equations and expressions with all of our various trig identities. And these skills will be essential when you go on to take calculus. So some basic rules for doing proofs with identities. You only want to manipulate one side of the equation at a time. This means that you can't clear denominators by multiplying everything by the common denominator and eliminating it. You can move everything to one side. You can't move everything to one-sided factor. You can't treat these like equations. Essentially, you can only manipulate one side at a time and show that you can get one side to match the other side. Now, you can manipulate one side by itself and then manipulate the other side by itself and then sort of meet in the middle so that you have algebraic expressions that are equivalent, so that you could essentially, if you think about like going down two columns and you meet at the bottom in the middle where they're the same, that you could go down one column and back up the other column in order to get back to the original expression. So you could only change one side of the equation at a time. These are not actually equations in the sense, because we don't know that they're equal to each other. We're trying to establish that. So no clearing expressions, no moving everything to one side. You can replace terms with other known identities to simplify an expression. Be aware of the target you are trying to reach at the other side of the equation. So some kinds of manipulations are more likely to get you there than others. Don't just do something because you know that you can do it. You want to think about strategy and sort of how do I get from point A to point B. It's often easier to choose the more complicated side of the equation to simplify rather than making the simpler side more complicated, since there's lots of ways that you can make things more complicated, and there are fewer strategies to use in terms of simplifying. Algebraic manipulations like finding a common denominator, multiplying by a quantity divided by itself, creating differences of squares, factoring on one side only are all fine. When using identities, try to relate trig functions that are naturally related to each other. So sine and cosine have Pythagorean identities, tangent and secant, for instance, cotangent and cosecant, or things that are reciprocals of each other, like tangent and cotangent, and so forth. Match all the angles in the expression. So if you have a double angle in one and not a doubled angle in the other, try to either make them all double angle or all single angle. When in doubt about what to do, particularly if you have more than two different kinds of trig functions in the expression, convert everything to sine and cosine. And then if it's possible to reduce a complicated or more than one term on one side of expression to a single term denominator, that is often helpful in canceling or separating terms. Now, after thinking about some of these general strategies, let's go ahead and look at some specific examples. So in this case, we have this 1 minus sine v, and that actually might be useful if it was 1 minus sine squared v, because then that would be a cosine identity. So we might be able to think about when you have a 1 minus trig function or a 1 plus a trig function, you may be able to multiply by a function divided by itself, where you can create a difference of squares. So in this case, we would maybe like to turn the 1 minus sine v into 1 minus sine squared v, because then we can replace the denominator with cosine squared, and then we have something in common with the other expression. And maybe we can then go from there. So for something like this, that may be an option that we can use. We might also want to rewrite the secant as 1 over cosine, which would suggest that, in fact, we do, in fact, want a cosine in our denominator. So converting this expression into something we can convert into a cosine is probably a good strategy. Now, we can, again, in print, I put a note here that this variable in this expression is technically the Greek letter nu. You can't really tell the Greek letter nu that much apart from the regular English letter V. So you can call this nu, you can call this V. In context, it's hard to tell, but don't use them in the same equation together. So in this case, I'm going to multiply the second expression here. I'm going to multiply it by 1 plus sine V and 1 plus sine V. So I'm multiplying by 1, so that's allowed. And then on this denominator, when I do this distributing, I'm going to get a difference of squares. That's my 1 minus sine squared. And then I can replace that denominator with cosine squared. And because I have, and notice I didn't distribute here, because I have cosine squared and I have a cosine here, I can cancel my cosine and one of these cosines. And then I just have the 1 plus sine V over cosine. And then I can have a common denominator, so I can add these two expressions together. I get 1 plus 1, my sines cancel, and I end up with 2 over cosine, which is 2 times secant. Again, this is another trick that you can think about. Don't necessarily FOIL everything just because you can, because in this case, we would have had to undo that in order to do the canceling. Now, another thing that you can use are Pythagorean identities. So if you can factor something out and replace it with Pythagorean identities, that will also help you simplify your expressions. So that is something that we can use here. So since we have combinations, we're trying to get secant converted into a tangent. The Pythagorean identity involving secants and tangents will become handy here. So the first thing that we're going to do in this problem, again, manipulating only one side of the equation at a time, is we are going to factor out a secant squared. This is the Greek letter chi. If we factor out a secant squared, then we're left behind secant squared minus 1. Secant squared is 1 plus tangent squared, and secant squared minus 1 from our Pythagorean identity is tangent squared. And when you distribute that back, you get tangent to the 4th plus tangent squared. All right, so now in this expression, we have 1 plus sine gamma over 1 minus sine gamma is equal to secant gamma plus tangent gamma quantity squared. Now, again, what is the more complicated side of the equation? I would say that if you're squaring something, that to me would be the more complicated side of the equation. So that's where I'm going to begin. So I'm going to start by rewriting my secant and my tangent as 1 over cosine and sine over cosine. Now, the reason for this partly is because my final expression has only sines in it. And since I have 3 different trig functions, they're not all related in a single identity. And so converting everything into sine and cosine is a way of reducing the number of different trig functions in your problem. So that's what I've done here. Now I can, because these have common denominators, I can rewrite this as this expression, and then I can apply my square to just the denominator and the numerator. So 1 plus sine gamma squared quantity squared and cosine squared gamma, since it's not multiple terms. Now we're going to undo the identity we actually used in a previous example. We're going to convert our cosine squared gamma into 1 minus sine squared. And then we're going to factor the difference of squares as 1 minus sine gamma and 1 plus sine gamma. We now can cancel one of our 1 plus sine gammas, and we are left with one copy of 1 plus sine gamma, and one copy of 1 minus sine gamma. Now, here we're using the Greek letter xi, or xi. It's been anglified to xi, and so that works perfectly fine if you don't want to make it 2 syllables and pronounce it more Greek-like. The Greeks don't actually have it. It's not a 2-syllable thing in Greek, but ks in English at the beginning of a word is weird. So xi it is. Here we're going to have to remember how to factor. And we may have to work with complex fractions. And by complex, I mean fractions inside of fractions, not complex numbers. But we would have to remember how to factor differences of cubes. And again, we have multiple different trig functions here. We've got sine and cosine on this side, and we've got secant and sine and tangent on this side. And so we're going to need to convert everything to sines and cosines. And so how are we going to do that? Well, we're going to start on one side and we're going to try to go from there. Now, you can work on both sides of the equation at the same time, only as long as you're only manipulating one side of the expression at a time, so that the algebra that you're doing doesn't involve both sides simultaneously. So here I'm going to start with my original expression on the left, and here I'm going to start with my original expression on the right. And I'm going to manipulate them both, but I'm going to just do sort of internal algebra. So on this side of the expression, I'm going to factor my cube. So my sum of cubes factors, if this is a cubed plus b cubed, this is a plus b, and this is a squared minus ab plus b squared. So a is sine, b is cosine. So we get this. And then I didn't do anything with my denominator yet. On this side of the expression, again, only manipulating the right side by itself, I'm going to convert my secants to 1 over cosine and my tangent to sine over cosine. Now, in the next step, I have my sine squared and my cosine squared. Sine squared plus cosine squared is 1, so I'm going to replace that with a 1. And then on this side of the expression, I'm going to get rid of these denominators. So I'm going to multiply the top by cosine and the bottom by cosine. So when I distribute here on the right, cosine times 1 over cosine is going to give me a 1, but cosine times sine is going to give me 1, it's going to give me sine times cosine. And then reverse on the bottom, cosine times sine over cosine is going to give me just the sine. The cosines will cancel, but then cosine times 1 is going to give me cosine. Now, there's a lot more going on here. I see I've got a 1 minus sine xi cosine xi, and I have a 1 minus sine xi cosine xi over here. So I want to try to keep that, but let's see what else that I can do. I've got some things going on in my denominator over here. Maybe I can do something with that. So over here, how do I get this sine xi plus cosine xi? Well, I've decided I can get my difference of squares by multiplying by sine and cosine, sine plus cosine and sine plus cosine on the top and bottom. That will get me this difference of squares on the bottom, sine squared minus cosine squared. Now I have my numerator is actually looking like this one, sine xi plus cosine xi, and 1 minus sine xi cosine xi. Okay, so my numerator looks good. How do I get my denominators to agree? Well, it turns out that this denominator we had before is actually similar to the cosine 2 xi formula identity, except that the order is reversed. So 1 minus 2 sine squared xi is the correct order, but this is the reverse order. It's 2 cosine squared xi minus 1 that I want. So I'm going to factor out a negative sign. And it turns out that this denominator is also a cosine 2 xi identity. It's just that it is also in the wrong order. So I'm going to also factor out a negative in order to put it into the correct order. And then this identity will become cosine 2 xi. And this identity will also become cosine 2 xi with that negative out front. Now here's another example. This is the Greek letter upsilon. Here's another example. So this one involves the double angle formula again. So we had the double angle formula that we used to make those things match. That's not the only strategy we could have used in the previous example, but that is one. In this case, we're going to need the cotangent double angle identity. So we're going to apply our double angle identity on the left side of the equation. And then we're going to rewrite our expressions in terms of sine and cosine. Now, then we want to find a common denominator. So look at our example that we have up here. We have cotangent and tangent. So how do we get cotangent minus tangent? Well, again, working from this right side, we want to convert everything over to this double angle formula. So rewrite as cosine over sine and sine over cosine. We're going to find a common denominator. So I'm going to multiply this one by cosine over cosine and this one by sine over sine. They both have sine and cosine in the denominator, so we can add them together. This expression is the cosine 2 nu formula. And this one is, if we had this 2, we pull that inside, then 2 sine times cosine is the double angle formula for sine of 2 nu, or 2 upsilon in this case. And so cosine of 2 upsilon and sine over 2 upsilon becomes cotangent of 2 upsilon. For sum and difference formulas, again, we want to think about applying them. This one doesn't have sum and difference angles in them, so we're going to use the sum and difference formulas to separate out our 2 angles on the left side here. So I'm going to apply my identity, and then I'm going to work with this denominator, see what I can simplify. Now, because I have a single component in the denominator and 2 pieces in the numerator, I can split these into 2 fractions. That will allow me to cancel, in this case, my cosine beta on this first term and my cosine alpha on the second term. And so now I have just alpha and beta left. Sine alpha over cosine alpha is tangent, and sine beta over cosine beta is also tangent. So tangent alpha plus tangent beta.